expression is this. So the second order total differential of z is just this. And mathematicians have worked out the conditions under which this quadratic form will be either positive, definite, or negative. And they are, for it to be positive, definite, this is h. h1 is just this. h2 is just this. And h3 is just the whole thing. So for this quadratic form to say be positive definite, the conditions are just this. All of these have to be positive. If all of those determinants are positive, that guarantees it's a positive definite quadratic. Now, the conditions for the second order total differential to be negative definite are that these alternate in sign of the first one being negative. So it's negative, positive, then this one would have to be negative. Now this same idea applies to cases where z is a function of x1, x2, x3, dot, 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 xn. The only difference would be this. You would have to add some more terms in the objective function. Dot, 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 xn. And you would need to add some more terms here. This first row would be dx1, dx2. Let me just do dot, 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 dx. And this matrix would now be this. It would be the full Hessian matrix for the n by n case. This would go, let me erase that and just do dot, dot, dot. And let me erase that and do dot, dot, dot. And this vector here would be n by 1. This would be a quadratic form now in variables. And the mathematicians have shown that the second order total differential can be expressed this way. And then what you need for your sufficient conditions for a positive definite quadratic form is for all of these to be positive. For a positive definite, you need that, you need that, you need this, dot, dot, dot. And the last one would be h sub n. Positive. All of those determinants of the leading principal minors are positive. Then the quadratic form is positive. Then you'll have a minimum. For a max, then this second order total differential is written the same way. But now the sufficient conditions for that to be negative definite are that those h1 be negative, h2 positive, H3 negative, dot, dot, dot. They alternate sign with the first one being negative. Okay. That would guarantee that this second order conversion is making it down. That would guarantee that you have a maximum at the critical value. Okay. Let me finish up today by just going through one problem, one economic problem with 3 choice variables. And actually the example I'm going to go over is quite simple. It's a price discrimination model again, where the monopolist can separate his or her customers into 3 groups. So,
before we
yes, Josh.
Since 1, 2, and 3 are just arbitrary names we name the variables, is it worth the trouble of like switching them around to get easier Hessian matrices to solve over?
Well, it is true. Is what you're saying, Josh, F12 is the same as F21?
No, I mean,
No. No.
we just arbitrarily named the variable x1 and the other one x2. So
Right.
if we wanted to switch them, we would get different Hessians to check for the determinants there. So would it be worth checking different ones to get, as long as they're all consistent? Could we look for ones that are easier to solve for the determinant?
Well, I mean, you could always redefine your variables. I mean, you could define x1 to be equal to, y2, or is that what you're saying?
We could just rename x2 to x1 and x1 to x2. And then we'd be solving for different determinants of different Hessians.
Yeah, but in order to keep it straight, let's just start with this case here, because we know if you follow this format, you know exactly what the second order total differential is. But then you're free if you want to redefine what x1, x2, x3 are. You can do that. But let's keep it, otherwise we'll very easily get confused. So the convention is to have the first variable called x1, the second variable x2, third x3. That way you know exactly how to check it. But then once you write it that way, you could redefine what x1, x2, x3 are. But to keep it straight, it's easiest just to do this. All right, let me go over a problem. An economic problem. Similar to the one we did at the beginning of class. Only differences, now there are 3 groups.
What are we selling this time?
What's that?
What are we selling this time?
Okay, widgets. We're producing widgets. And we can separate our customers into 3 groups. And the 3 groups have the following demand functions. Group 1, same as before. $100 minus Q1. That's the inverse function. Group 2, same as before. 80 minus Q2. Group 3, 60 minus Q3. We can separate those 3 different groups and charge them different prices. Maybe group 1 is non-students. Well, you could just think of it 3 groups. I'm not going to just 3 groups. Maybe you have students, non-students, senior citizens. And then hopefully the senior citizens are not students, so that wouldn't be a problem. Three different maps. Okay, so this is the demand for non-students, students, senior citizens. Okay, and let's assume there are no senior citizens or students. Okay. So those are three distinct groups. The cost function, again, let's just use this. Only now Q is Q1 plus Q2 plus Q3. Total output is the amount you sell group 1 plus the amount you sell group 2 plus the amount you sell group 3. How is the price discriminating monopoly going to decide how much to sell to each group and what prices to charge each group? We assume the monopolist wishes to maximize profit. So now we want to get a profit function, and this profit is going to be expressed as a function of what three variables? What'd you guess? Q1, Q2, and Q3. You could do this problem as a function of P1 and P2 and P3. But the easiest way to do it is a function of Q1, Q2, and Q3. Of course, that requires that we eliminate P1, P2, and P3, but that's easily done. What is our revenue function?
P1 times Q1
P1, Q1?
plus P2, Q2 plus P3, Q3.
Yes. And notice, if you eliminate P1, substitute in for P1, it's going to be 100 minus Q1 in parentheses times Q1. So that'll be 100 Q1 minus Q1 squared. Plus this term here, P2, Q2 is going to be 80 Q2 minus Q2 squared. And this last term is just going to be 60 Q3 minus Q3 squared. That's revenue expressed as a function of Q1, Q2, Q3. Cost is already expressed as a function of Q1, Q2, Q3. Therefore, profit is just revenue minus cost, and the cost is simply going to be minus 20 Q1 minus 20 Q2 minus 20 Q3. So profit, let me emphasize, it's expressed as a function of Q1, Q2, and Q3. Is simply, we've got 100 Q1 minus 20 Q1, that's going to be 8 Q1. Minus Q1 squared. We've got 80 Q2 minus 20 Q2, so this is going to be 60 Q2. Minus Q2 squared. And we've got a 60 Q3 minus 20 Q3, that's 40 Q3. Minus Q3 squared. Here's our profit function, expressed as a function of Q1, Q2, and Q3. Now, what are our first order conditions? The first order conditions are pi 1 equals 0. And pi 1 is just 80 minus 2Q1. Set that equals 0. Pi 2 is just going to be a 60 minus 2Q2. Put that equal to pi 3 is just a 40 minus 2Q3. And in this case, it's very easy to solve. This term, this equation only involves Q1, so you get Q1 0. Critical value of Q1 is 40. Critical value of Q2 is equal to 30. The critical value of Q3 is equal to 20. Right? Now, how do you check to make sure you have a maximum? What is it you are going to need to start off with? Actually, yeah. Okay. You need your all your second derivatives in order to form your Hessian. Now, your Hessian matrix would just be this. Pi 1, 1, pi 1, 2, pi 1, 3. Notice we switched from pi to f. Before it was f, but now our objective function is pi. So that's the only difference. Then you need a pi 2, 1, pi 2, 2, pi 2, 3, pi 3, 1, pi 3, 2, pi 3, 3. And then you need H1. The determinant of H1 is just this. It's just whatever pi 1, 1 is. H2, the determinant of H2 is just this determinant. And then H3 is the determinant of the whole thing. Okay, just the determinant of this whole thing. I'll just put H here. I've already written it. Okay, so you got to get all these second order derivatives. Figure out what H is. Now, what is pi 1, 1? What is pi 1, 2? Notice pi 1, 2, well, okay, just tell me, what is pi 1, 2?
0.
0. If you go to pi 2, notice there's no Q1 there. So pi 1, 2 is 0. This is going to make it easy. What is pi 1, 3?
0.
Also 0. You differentiate this with respect to Q1. 0. Okay, let's do the next row. Pi 2, 1.
0.
0. By the way, pi 2, 1 is equal to pi 1, 2, that's 0. Pi 2, 2.
-2.
Negative 2. Pi 2, 3.
0.
Also 0. Pi 3, 1.
0.
0. Pi 3, 3. Oh, excuse me, pi 3, 2. 0. Pi 3, 3. Negative 2. All right, so our Hessian matrix is just this. I substitute in. That's a -2. That's 0. That's 0. That's a 0. This is a -2. That's a 0. Pi 3, 1, which I erased, that's a 0. Pi 3, 2 is a 0. Pi 3, 3, -2. H sub 1 the determinant of the first principal minor, leading principal minor, is pi 1, 1, that's minus 2. That's negative. What is this term right here going to be? You just substitute in. This is a minus 2. This is a 0. 0. This is a minus 2. So what is this equal to?
4.
4.
So you have a negative.
Oops. Sorry. That's a 0. See, H2 is just these 4 elements. So minus 2 times minus 2 is 4. And minus 0. That is positive. What is the determinant of the full thing? Well, let's just expand across the first row. And we're doing the determinant of this. So let me change these to be vertical lines. Then this will be the determinant. And H and H3, same thing. Okay. So expand across the first row. You take minus 2 times its minor. And what is the minor of this element right here? It's going to be?
Minus 2, 0, 0.
Yes, we have these 4 elements. And what is this minor equal to?
We just calculate that to be 4.
4. Now the next 2 elements are zeros. So you're done. So if you expand across the first row, all you do is take this element times its minor. Delete that row, that column, you're left with this. And the determinant of this 2 by 2 is 4. So it's minus 2 times 4, minus 8. So the pattern is the first leading principal minor is negative, second one's positive, third one's negative. Therefore, the second order sufficient conditions for a maximum are satisfied. And we have a maximum here. Because H1 is negative, H2 is positive, H3 is negative. So we know that profit will be maximized at this critical point. If you go back to your objective function and plug in those values of Q1, Q2, Q3, that gives you the maximum profit. And that means in terms of prices, remember P1 was 100 minus Q1, so P1 star is 60. You should charge group 1 $60. You should charge group 2, since P2 was 80 minus Q2. Q2 was 30, wasn't it? So this should be 50. The price for group 3 should be, since their main curve was 60 minus Q3. Q3 was 20, wasn't it? So you should charge them 40.